Welcome to Chronicles of the Bioverse, where we uncover the fascinating stories of life and the natural world around us, from the tiniest nanoparticles to the vastness of the universe,
making the minuscule monumental.
In this series, Nanomaterials, we dive deep into the world of nanotechnology to explore its profound impact on our daily lives. Episode 2, From Atoms to Products.
making nanomaterials.
In the previous episode, we discussed how Dr. Richard Feynman laid the foundations for nanotechnology in his talk, There's Plenty of Room at the Bottom. In the talk, he discussed how he believed we could use machines to create even smaller and smaller machines. Once word got out, and other scientists started gaining interest in this new field of science.
Two main approaches were developed for the production of nanomaterials. These were the top-down and bottom-up approaches.
In this episode, we dive into the production of nanomaterials with both these methods, and we will talk about how using different techniques to produce nanomaterials can potentially make them less toxic.
The top-down method involves breaking the bulk materials, such as pieces of gold, silver, etc., into very small nanoforms.
This is generally done by physical methods, such as milling or grinding, or lithography, the use of light ions to split the bulk material into nanomaterials.
These methods generally result in nanomaterials with a well-defined size and shape, and can also be used to give the nanomaterials unique catalytic properties.
However, all methods do have their disadvantages. For starters, the top-down approach doesn't really allow us to produce nanomaterials uniformly on a large scale. Additionally, the nanoparticles can also be contaminated or start to stick to each other during this process, which is also not good in terms of reproducibility.
To overcome some of these challenges, advanced techniques such as precision engineering have been developed and are being improved by the industry. Precision engineering is crucial in the production of microelectronics and allows us to produce structures and machines that are repeatable and remain stable over time. Precision engineering also allows us to exhibit dimensional control within very tight tolerances during the process of manufacturing.
But the top-down approach remains rather expensive and takes a considerable amount of time. The bottom-up approach involves building the nanostructures one atom or molecule at a time. This can be done by using different chemicals and is based on the principle of molecular self-assembly, which is the spontaneous formation of stable structures at conditions near thermodynamic equilibrium. Using the bottom-up approach, one can essentially grow nanomaterials through the self-assembly of atoms or molecules. One of the major bottom-up techniques for creating nanostructures for electronics is chemical vapor deposition, in which a gas is deposited onto a substrate as a thin film and then etched out. This method has the finest degree of control and is repeatable. Due to its simplicity, the sol-gel method is the most common method of nanomaterial synthesis. In this method, tiny particles are suspended in a liquid to form a sol.
The particles start sticking to each other over time, forming a jelly-like gel, which is then dried and sometimes heated to change its shape or size.
The bottom-up approach is generally more cost-effective than the top-down approach and can produce larger quantities of nanomaterials.
It also allows fine control over the size and shape of the produced nanoparticles.
Other than the top-down and bottom-up approaches, the synthesis of nanomaterials can also be categorized as physical, chemical, or green synthesis.
Physical synthesis makes use of physical techniques, like milling or grinding, to produce nanomaterials generally from the bulk material. These are commonly employed in the top-down synthesis of nanomaterials. Chemical synthesis refers to the use of chemical methods, such as chemical vapor deposition or the sol-gel method, to produce nanomaterials.
These are generally used in the bottom-up approach. Green synthesis is also a bottom-up technique which uses natural sources, like plants, bacteria, and algae, to produce nanomaterials. Green synthesis does not involve the use of dangerous chemicals and toxic solvents and is environmentally friendly. Green synthesis is generally used to produce metal and metal oxide nanomaterials. Extracts from plants, algae, etc. contain enzymes that are able to oxidize metals, so adding these extracts to solutions containing ionic metals results in the formation of nanomaterials as the metal atoms start sticking to each other.
Recently, green synthesis has gained popularity due to its sustainability. These methods do not require copious amounts of energy or money, and produce less waste.
Using extracts from different plants or organisms may potentially also result in less toxic nanomaterials being produced. But not all nanomaterials are synthesized in a laboratory. Nanomaterials can also occur naturally or incidentally.
Natural nanomaterials are formed by biological, geological, or atmospheric events, such as volcanic eruptions.
Sea spray can also generate nanomaterials when the ocean water interacts with the atmosphere.
And let's not forget about all the tiny proteins, viruses, and other biological entities that exist in the nanoworld.
In Victoria Land,
East Antarctica, flowing from the Taylor Glacier is what is commonly called blood falls.
Here, bacteria living inside the subglacial lake produce iron nanospheres which oxidize when they come in contact with the environment, resulting in the Erie Red waterfall.
Incidental nanomaterials are nanomaterials that have been produced as a byproduct of human activity. The burning of fossil fuels forms nanomaterials, and so do industrial processes such as welding and smelting. Pollution, of course, also releases nanomaterials into the environment. Because incidental nanomaterials are so abundant in our environments, we take them up through ingesting them, inhaling them, and even through our skins. It is therefore very important that we understand the long-term health risks associated with nanomaterials, since our exposure to them is unavoidable.
In the next episodes, we will discuss the uses of nanomaterials and how they may be harmful to our bodies and the environment. Thank you for watching. If you enjoyed, please consider liking and subscribing. And don't forget to turn on notifications so that you don't miss the next episode of Chronicles of the Bioverse.